In part 3, what we'll be talking about is ionic compounds and the solubility of ionic compounds in water. Okay, so at this point, I hope we know that an ionic compound is going to be composed of a cation and an anion. Okay, and that these will be conjoined by an ionic bond. So a bond connecting one thing that possesses a positive charge, i.e. a cation, and one thing that possesses a negative charge, i.e. an anion. Okay. Now in this case, we're going to be talking about ionic compounds, solubility, and also precipitation reactions. And the good thing is that we've already really talked about the idea of complete and net ionic equations, so we don't have as much to talk through here. I just want us to work through a few examples of looking at ionic compounds, figuring out whether they would each be soluble in water, and then identifying whether or not reactions will happen when we mix different types of ionic compounds. So let's look at a few examples of these. If you would like to follow along in your textbook, you can look at example 5.5 on page 181. So I'll note that down. These are going to be from example 5.5 on page 181. I also do recommend that you pull up somewhere table 5.2, table 5.1, which is on the other page, the opposing page, that's page 180. Okay, so here you can find all of the solubility rules for a variety of ionic compounds. These would be really good to have next to you as we discuss this section. And as a reminder, you will not have to memorize these rules for the exam. You'll be provided them. Okay, but I still want you to practice them ahead of time so that you're not having to take up some of that time on the exam refreshing yourself on where something is in the table. Okay, so let's start with example 5.5, and we see 4 different compounds here. Okay, I'm just going to copy them down up here so that you can follow along without having to look right where the answers are shown. Okay, I'm going to write out each of these 4. I want us to practice naming them, and then I want us to identify whether or not they're going to be soluble. Okay, so for each of these, and let's number these as well. We'll say that this is 1, 2, 3, and 4. So this first one, well, the two elements that we have present are lead and chlorine. So let's figure out how we'd name this. It's an ionic compound, so we might suspect that we can at least start by putting down the names of the metal and of the nonmetal here. But because it's just a single element, we're going to change its name a little bit. We're going to change it from chlorine to chloride. And because lead in this case takes on multiple possible charge states, we're going to have to name this one. Okay, so this one is going to be specifically lead 2 chloride. The reason for that is that this is going to split off into lead 2 plus, and this is going to split off into Cl minus, but of course we're going to have 2 of them here. So I'll put a 2 in front of it. That's not really part of the species itself, it's just to indicate that we have 2 chloride anions. Okay, but because this is lead 2 plus, we call it lead 2. So how would we figure out if this is soluble or not? Well, let's consult table 5.1. Okay, I want you to look at table 5.1 on page 180, and what we see is that, first of all, I'm looking at the upper part of the table, and I see that chlorine, bromine is, well, let me be more careful, the chloride anion, the bromide anion, and the iodide anion are all indicators that if a compound contains one of these, it's probably going to be soluble. But this one, these chlorides, actually do have some exceptions here. Okay? By contrast, right, if I looked at something like NaCl, right, this splits into Na plus and Cl minus, well, this Na plus, the very first row in the table, tells me that if a compound contains lithium, sodium, potassium, or ammonium, that all of these are going to be soluble, with no exceptions. So sodium chloride will be soluble. Okay? So if we look back at our example of lead 2 chloride, I see that chloride is usually going to be soluble, except if it pairs with certain types of ions. Now, is the one that we're looking at one of those? Well, I see silver plus, that's the first one there. I also see mercury 1. It might confuse you at first because it says Hg2, 2 plus. So why is it mercury 1? Well, because there's 2 mercury atoms there with a total charge of +2. So each of the 2 mercury atoms has a charge of +1. So we call it mercury 1 chloride. Or, well, we're not looking at mercury chloride in this case. We would call that ion, though, mercury 1. But I also see lead 2 plus as one of the exceptions to the general rule that chlorides are usually soluble. In this case, it seems like if chloride pairs with lead 2 plus, the resulting compound will be insoluble. Well, in this case, that's exactly what we have. Right? This here is lead 2 plus. So in this case, it looks to me like this compound is going to be insoluble. If you put lead 2 chloride in water, it's going to stay as a solid compound and not dissolve. Okay? So let's look at this next one. Copper chloride. Well, copper is another metal that sometimes forms different charge states. So let's name this as copper. Well, we've got 2 chlorides, each one with a -1 charge. So this copper must be copper 2. Why? Because it's copper 2 plus, and we have 2 Cl minuses, 2 chlorides here. Right? So because it's copper 2 plus, we call it copper 2. Not because there's 2 chlorides, but because it's copper 2 plus. Okay, so copper 2 chloride. Now, how about this one's solubility? Well, if I look at the table again, I'm again looking at the top part of the table, row 3, and I see that chloride, bromide, and iodide are usually going to be soluble in ionic compounds. I do see those exceptions we talked about for silver and for mercury 1 and for lead 2. But copper 2 is not one of them. Copper 2 chloride appears to be soluble. Okay? So if you put copper 2 chloride into water, it will dissolve. It'll split apart into Cu2 plus ions and into Cl minus ions. Okay, how about this third one? Well, this one contains a polyatomic ion, NO3. To figure out its charge, we could recognize that Ca will always form a 2 plus charge. So if this is calcium 2 plus, then this bit over here, NO3 minus, that has 2 of them, right, that subscript 2 only applies to the parentheses, not to the calcium. So there would be 2 nitrates here. So this molecule, or this compound rather, we would call this calcium nitrate. I want us to remember there's no need to put this as calcium 2, even though it's calcium 2 plus, because all calcium ions will form 2 plus cations. Excuse me, goodness. All calcium will form 2 plus cations. So there's no need for us to over-specify the charge there. It's implied by the fact that it's calcium. Okay. Sorry, it's bugging me. Okay. So how would we figure out if this one's soluble? Let's look at our table. All right, what I see on row 2 in the upper part of the table is that a nitrate, anytime you have nitrate in an ionic compound, that ionic compound will be soluble with no exceptions. And calcium, well, certainly no exception. So this compound here, calcium nitrate, is also going to be soluble. Let's look at our last example here. We have another polyatomic ion. So let me first identify the one that we should be able to figure out with no ambiguity. Barium is a metal that's in the second column, making it an alkaline earth metal. So it's always going to have a +2 charge. So what's this other bit here? Well, this is going to be sulfate. Okay, so sulfate will be SO4 2-. Let's look at our table. What I see in the first part of the table is that on row 4, sulfate is usually an indicator that a compound is soluble. Now there are some exceptions. Let's look on the list there. What I see is that when sulfate pairs with strontium 2+, barium 2+, let's make a note of that. That will affect this compound we're looking at, but let's just look at the rest of those rules first. When sulfate pairs with strontium 2+, barium 2+, lead 2+, silver+, or calcium 2+. For any of those metal cations, sulfate will be insoluble when it pairs with it, and barium is one of them. So barium sulfate, which again does not need to be called barium 2 sulfate because all barium will form a 2+ charge when it's an ion. Okay, so this compound here is one of the exceptions to the general rule of sulfate solubility. So this one will be insoluble. Okay. Now there's a couple other examples right underneath example 5.5. You'll see these as for practice 5.5. Let's talk through them really quickly. For A, you see NiS. How would we name that? Well, that would be nickel sulfide. But which nickel? Well, if sulfur is there, sulfur will always have a -2 charge. So that must be nickel 2+ or nickel 2. So that would be nickel 2 sulfide. Now, the sulfur bit there. Okay, if I look at our table, on the bottom part of the table this time, these indicate that compounds with these ions are usually not soluble. Okay, so sulfate, I see S2- there. It looks to me that there are a whole bunch of exceptions there, but if I look through carefully, I don't see nickel on there. So to me, nickel 2 sulfide, NiS, that's part A for practice 5.5 on page 181. Nickel 2 sulfide must be insoluble. Okay, how about the next one? Well, that would be magnesium phosphate, is how we would name that. Let's look on our table for a clue about that. I don't see anything about magnesium in any of these rows, but I do see phosphate there at the very bottom of the table. It looks to me that if phosphate or carbonate, if an ionic compound contains phosphate or it contains carbonate, it's probably going to be insoluble. Is this an exception? Well, is magnesium one of the exceptions? No, it doesn't look so. So that's just going to be an insoluble compound. Okay, how about the one right after it? Lithium carbonate, that's part C. Well, carbonate is at the bottom of the table, and it looks to me that carbonates are usually insoluble. But, okay, if it pairs with lithium, sodium, potassium, or ammonium, that's that NH4+. In that case, it'll be soluble. Okay, so lithium carbonate, yeah, that's one of those exceptions. So lithium carbonate will be soluble. Okay, last one here. This is part D. This is ammonium chloride. Well, here we can actually figure this out from the top of the table. If something contains ammonium, it's always going to be soluble. NH4+, always soluble. Okay, so cool. Now we know how to identify whether something is soluble or not. Here's what I'd like for you to do. Take a moment, pause the video, and look at figure 5.13, which is on page 182. So please pause and take a moment to look at that. I'm going to resume. I'll talk through that after you unpause. Okay, so in figure 5.13, we're looking at what's called a precipitation reaction. In this reaction, what you see is that two compounds are being mixed. The hand here is holding a small, like a small glass container that contains potassium iodide, Ki. Okay? When you mix that with what's shown here in the bottom in the flask, which is lead nitrate, it looks specifically to be lead 2 nitrate. Okay? When you mix these two things, each of those two compounds on their own is soluble. Well, how do we know that? Potassium iodide, let's go back to the table on page 180. Potassium is in that very first row. It looks to me like if something contains potassium, it's going to be soluble. So potassium iodide, no problem. That one's soluble. How about the lead 2 nitrate? Well, on row 2 of the table, it looks to me like if something contains nitrate, it's going to be soluble. So potassium iodide, the thing that's in the thing that hand is holding, and lead 2 nitrate, which is the liquid, the clear liquid in the flask, these are both two completely soluble ionic compounds. When you put one of these ionic compounds in water, it dissolves. It dissolves completely into the ions that make it up. Okay, but when they mix, now you have 4 types of ions in solution. What do you have? You've got K+, as you see in the circle on the left there. You've got I-, as you see in the circle on the left. You've also got nitrates that were there in the lead 2 nitrate, and you've got the lead 2 cations. These 4 species can all bump into each other. And I want you to pause for another second and think about what would happen if each of these bumped into one of the others. So consider for a moment, consider every pair of K+, I-, Pb2+, that's lead 2+, and nitrate. Okay, I'm going to hope at this point that you've paused and thought about that for a moment. Well, there's 4, let me see. There are, oh God, I don't remember my combinatorics very well, right? But there's a whole bunch of different combinations here. We could have the potassium pairing up with the iodide. We could have the potassium pairing up with the lead 2. We could have the potassium pairing up with the nitrate. We could have the iodide pairing up with the lead 2+. We could have the iodide interacting with the nitrate. And finally, we could have the lead 2 interacting with the nitrate. Let's consider each of those possible interactions in turn. So the very first one, what would happen if a potassium cation, K+, interacts with an I-, an iodide anion? Well, they could form potassium iodide, it's true, but they would just dissolve again, because we already know that potassium iodide is water soluble. Okay, the potassium could bump into a lead 2 cation, but they're both cations, they're both positive. So they're just going to push each other away. They're not really going to do anything. We could see the potassium meeting up with the nitrate, so the K+ meeting up with NO3-. But if that happened, right, we already know from table 5.1 that potassium nitrate would be soluble because it contains 2 types of ions that are soluble themselves without exception. Okay, so the potassium really can't react in a way that sticks with anything here. All right, in other words, the potassium by and large is just going to be floating around freely in solution. Okay, the iodide now. We've already covered what the iodide could do with the potassium, so let's skip that. What if the iodide interacted with lead 2? Well, that would form PbI2. That would be lead 2 iodide. Let's look at our table again. It looks to me like iodide is usually soluble, but if it pairs up with lead 2, it's going to be insoluble, and that's what we have here. So every time a lead cation, a lead 2 cation, meets up with an iodide anion, they form an insoluble compound. And you can see that in the third circle here, right? That's that alternating gold and blue lattice here. That's lead 2 iodide, and because it's not soluble, every time it forms, it doesn't dissolve again. That lead cation leaves solution. it falls out of solution like a precipitate. In fact, lead to iodide in this case is a precipitate. Hence why this whole thing at the top of the page on the upper left, you see this called a precipitation reaction. Okay, so every time one of these forms, the lead cation drops out of solution, the two iodide anions drop out of solution, and you form a solid precipitate. So let's just trace out quickly the rest of these things that might happen. If an iodide bumps into a nitrate, what's going to happen? They're just going to push each other away because they're both negatively charged. Okay, so that's not going to do anything. And how about the last possible interaction here? Lead-2 interacting with nitrate. Well, it can happen, sure, right? It could form lead-2 nitrate again. But we already saw that if it forms, it'll just dissolve just like it did in the first place. So if that's the case, we now know that of all of these possible interactions, the only one that is stable enough to stick around is the lead-2 iodide, which is why if you were to mix potassium iodide with lead-2 nitrate, you form one insoluble compound that drops out of solution, and one soluble compound, potassium nitrate, that just goes right back into the solution, right? It just stays dissolved. Now let's look at an example where no reaction happens. I'd like you to turn your attention to figure 5.14 on the next page. This is page 183. Okay, so here we see a test tube that contains potassium iodide is being poured into a beaker of sodium chloride. And just visually, right off the bat, we can see that whereas in figure 5.13, there was this brilliant yellow color that appears in the solution, in 5.14, nothing seems to be happening. So why is that? Well, if we look at potassium iodide and sodium chloride in this case, let's again consider all the possible interactions. I'm going to ask you one more time to pause and think about the different types of interactions that could happen here. So we have a few different pairs that could interact, right? We've got potassium and iodide that could interact again, but if they do, they're just going to redissolve. We have potassium and sodium that could interact, but since they're both metals, they're really just going to push each other apart. We have potassium and chloride that could interact, and if that happens, you could, in theory, form potassium chloride, but it'll just redissolve. We can see that because of table 5.1 on page 180, right? Potassium, if it interacts with chloride, it would just redissolve again. Okay, so what's left? We've got iodide and sodium. Well, sure, sodium iodide could form, at least for a moment, but sodium iodide, according to table 5.1, would just redissolve again. So that one's not really going to happen. And iodide and chloride could interact, but if those two happen, being both negative, they'll just push each other away. So finally, sodium and chloride could interact, but if they interact, that's just going to dissolve again, just like we know it would. In fact, just like it did in the first place. So in other words, at the start of this, you have 4 ions that are all floating around in solution. And at the end of this, you have those same 4 ions still floating around in solution, right? Because although they're all interacting, anything that forms redissolves again just as fast. So that's why in this case, we would really say no reaction happens. It's kind of an oversimplification. I mean, yes, things are forming and redissolving again. It's not like it's static in the beaker and that nothing's moving around and nothing's interacting. But we say that there's no reaction because if we were to look at the net ionic equation, there'd be nothing happening there. Let's take a look at what I mean, okay? So I'm going to scroll down just a little bit here. We're going to return back. We're still going to be looking at these 2 examples, but we're going to return back to the screen here. So let's write out these 2 reactions. I'm just going to copy down the reaction shown on page 182. So this would be 2 potassium iodide aqueous reacting with 1 lead 2 nitrate. And remember, we're not going to put the Roman numerals here because we only put those in the name, not in the formula itself. So that one's also aqueous. And this is going to react to form this is going to react to form lead 2 iodide. And this one's not going to be aqueous, actually. This is going to be solid. Plus 2 potassium nitrates. This one will be aqueous again. Now we've just written out here the molecular equation. Let's go from here and try to write out the complete ionic equation. So we know that the potassium iodide is going to split up. So we're going to have 2K plus and 2I minus. We know that the lead nitrate is going to split up. So we'll have a lead 2 cation, aqueous, and we'll have 2 nitrate anions. These will also be aqueous. Right, and on the product side, our lead 2 iodide is solid. So this one's not going to split apart again. It's not insoluble after all. I'm sorry, it's not soluble after all. But the potassium nitrate will. This is going to split apart into 2 potassium ions and 2 nitrate ions. And so this is what we could label our complete ionic equation. Let's isolate the spectator ions here. It looks to me like the potassium exists in the same form on both sides, and that the nitrates exist in the same form on both sides. So our spectator ions in this case, which need to be removed if we want to write the net ionic equation, our 2 spectator ions will be K plus and NO3 minus, or nitrate. Okay, let's take them out and see what we have left over. Okay, so it looks to me like what's left, I'm going to rearrange it just to put the cation first. So lead 2 plus aqueous plus those 2 iodides that I just skipped over. And those are going to react to form lead iodide. Okay, good deal, right? So now we have this reaction written out. And we now know for this reaction, for this precipitation reaction, what the net ionic equation would look like. Okay, so let's take a second then and consider the reaction that's shown on page 183, right? Because this is the reaction from page 182. Here, we're going to have from page 183, Ki, and I'm going to complete the reaction that's written there, just so we can see how this would shake out. So we have Ki aqueous plus NaCl aqueous, and let's say that these would swap to form sodium iodide, which if I look at the table, right, we could copy down these 2 aqueous markers here, but if I look at table 5.1, we can figure out that sodium iodide would be aqueous, and we can also find out that potassium chloride would be aqueous. So let's write the let's write the complete molecular equation here. We're going to have K plus aqueous plus I minus aqueous plus Na plus aqueous plus aqueous chloride here. Now on the product side, well, sodium iodide is aqueous, or I'm sorry, is soluble. So let's go ahead and write that as aqueous sodium plus and aqueous iodide and, well, potassium chloride, also aqueous because that one's soluble. So this will be K plus aqueous plus Cl minus aqueous. All right, let's identify our spectators. It looks to me like K plus is the same. Okay, how about I minus? Yeah, that one looks like it's the same. Okay, if I check sodium, if I figure out where my cursor is, that one seems to be the same. And I need one more color here. How about chloride? Yeah, that one also seems to be the same form. So it looks to me like we've got quite a lot of spectators for this one. I've got K plus, I've got I minus, and in fact, looking at it, it looks like everything here is a spectator, right? So I want you to imagine, as I'm finishing writing these up, what our net ionic equation is going to look like. Because remember, when we write that, we have to take out everybody who's just spectating. So the net ionic equation, well, nobody's left over. That's going to be, well, that. You know, there's nothing to go here. So let me, instead of putting question marks, put an X here just to remind us that there's not even really anything left over here. And the same thing is true on the product side. This is why when all of the species present are soluble and they don't form a precipitate, this is why we say that in this case, no reaction occurs. Okay? All right, so that tells us a little bit about different types of precipitation reactions. Okay, what I'm going to ask for you to do as the quiz question for this section, let's go back over to where we have all of these listed out. Here, I'm going to ask you to synthesize some stuff for me. I want you to write an example of one balanced precipitation reaction and one balanced example of mixing two aqueous ionic compounds that do not have a reaction occurring. So let me repeat all of that here and try and clarify that. So for question 1 here, please write an example of a balanced precipitation reaction that was not in this lecture. Okay. Oh, before I do that, so to clarify, what I'm looking for in this case is a reaction with two aqueous species, so soluble species, that react to form one aqueous compound and one insoluble compound. And let me clarify something. When I say that, what I'm talking about is two aqueous ionic compounds. Okay, so again, that needs to not be from this lecture. I want you to spend some time thinking about that. I also want you to give me an example of two ionic compounds that will not react. In other words, they do not form a precipitate. And this is specifically going to be two that do not form a precipitate when mixed in water. I'm going to say the example should not be from this lecture either. All right, so that's going to bring us to the end of this section. I've got one more that I want to talk about here, but thankfully that one's not going to be very long. So let's just go ahead and wrap this one up, and I'll see you in the last section.